Have you ever thought about what holds atoms together in a molecule, whether it's in water, sugar, or even oxygen gas? That invisible force keeping atoms united is what we call a chemical bond. A chemical bond is the force or linkage that binds two or more atoms to form a stable molecule. But why do atoms bond at all? It all comes down to one thing: stability. Atoms are like people seeking balance. Just as we form relationships to feel complete, atoms bond to attain a stable electronic configuration, often mirroring the electron arrangement of noble gases. These chemical bonds are of two main types: electrovalent, also known as ionic, and covalent bonds. Whenever you see atoms forming molecules like sodium chloride or methane, remember they're simply obeying the rules of chemistry to achieve stability. Let's now take a closer look at the noble gases, the silent guardians of chemical stability. Elements like helium, neon, and argon have something special. Their outermost electron shell is completely filled. Helium has two electrons in its only shell, while neon has an electronic configuration of 2,8, which means two electrons in the first shell and 8 in the second. This pattern continues with heavier noble gases like argon and krypton. This full outer shell makes them extremely stable and unreactive. For example, argon has the electronic configuration 2,8,8, that's 8 electrons in its third shell, satisfying the so-called octet rule. That's why these gases are often found in their elemental form and rarely form compounds. They don't gain, lose, or share electrons, they simply don't need to. Think of them as the chemically content elements of the periodic table. But what about the other atoms? Why are they so eager to react? Atoms that are not noble gases have incomplete outermost shells. This makes them unstable. For instance, a sodium atom has just one electron in its outermost shell, which makes it desperate to lose that electron and become like neon with a full octet. Likewise, chlorine has 7 electrons in its outer shell, just one short of 8. So, it readily accepts an electron to become like argon. This difference in stability drives chemical bonding. Atoms either lose, gain, or share electrons to imitate the stable electronic configuration of noble gases, and in the process, they become more stable themselves. That's the entire basis of why chemistry happens. Now, let's decode the two golden rules that atoms follow while bonding: the duplet rule and the octet rule. The duplet rule applies mostly to small atoms like hydrogen and helium. They aim to have just two electrons in their outermost shell. For example, each hydrogen atom shares one electron in a hydrogen molecule, so both achieve a duplet. For other atoms, the octet rule dominates. Atoms try to have 8 electrons in their valence shell. Take oxygen. It has 6 electrons in the outer shell. It shares 2 electrons, forming 2 covalent bonds and reaching an octet. So, whether it's hydrogen or oxygen, atoms play the electron game to either hit 2 or 8 electrons in their outermost shell. That's the chemistry of stability. As we'll soon see, how they achieve this, by transfer or sharing, decides the type of bond. Let's now explore the two pathways atoms take to form chemical bonds: electron transfer and electron sharing. In ionic bonding, also called electrovalent bonding, atoms transfer electrons. For instance, sodium donates one electron to chlorine. Sodium becomes a positively charged ion, Na+, and chlorine becomes Cl-. The electrostatic force between them forms sodium chloride, an ionic compound. In covalent bonding, atoms share electrons. A classic example is the oxygen molecule, where two oxygen atoms share two pairs of electrons, forming a double covalent bond. So, in simple terms, ionic bonds are born from giving and taking, while covalent bonds are all about sharing. These are nature's strategies to satisfy the duplet or octet rule, and to keep atoms happy. Now, here's where periodic properties step into the spotlight. The formation of chemical bonds is influenced by three important factors: ionization potential, electron affinity, and electronegativity. Ionization potential is the energy required to remove an electron. The lower it is, the easier it is for a metal to lose an electron, perfect for forming a cation in an ionic bond. Electron affinity is the tendency of an atom to gain electrons. A higher value means a nonmetal readily becomes an anion. Electronegativity is the pull an atom exerts on shared electrons. A large difference in electronegativity between two atoms, say sodium and chlorine, leads to an ionic bond. A small difference, like in hydrogen and chlorine, leads to covalent bonding. So, periodic trends don't just make the table colorful, they're the force behind every bond in chemistry. Let's quickly revise what we've learned about chemical bonding. Atoms form bonds to achieve a stable electron configuration, either a duplet like helium or an octet like neon. They do this by transferring electrons in ionic bonds or sharing them in covalent bonds. Noble gases show us what stability looks like: full outer shells that make them unreactive. In contrast, other atoms form bonds because their valence shells are incomplete. The nature of the bond depends on periodic properties like ionization potential, electron affinity, and electronegativity. So remember, every molecule you see, from salt in your kitchen to oxygen in the air, is held together by these tiny yet powerful chemical bonds. I hope this session helped you see how chemistry is more than just electrons and shells. It's the reason behind matter's structure, function, and transformation. Catch you in the next session where we explore the fascinating world of electrovalent bonding, electrovalent compounds in even greater detail.